Morning, everyone. Let's start. Today, we will talk about prefetching. Um, we studied on cache and DRAM. We know that cache is faster and DRAM is slower, so that we hope every piece of data we want to read, we want to fetch is in the cache. We have a cache, more cache hits. In this way, we don't need to frequently access the DRAM off-chip main memory. We have a better performance, but unfortunately, this is not. Sometimes this is not possible. Um, this is the reason why we need some scheme named prefetch. So the meaning of prefetch is to read the piece of data or fetch the block ahead of the demand. Demand means you have a cache miss. You actually read that piece of data and then you cannot find that piece of data in the cache. So there are three types of misses. Compulsory means you never, access that piece of data before. So this is a totally new data. You don't have it in the cache. The second one is a capacity. Because of the limitation of a capacity, you cannot hold all the data you need for this application in the cache. So sometimes you have to, you know, thrash the entire cache. You always miss the data you want to read. And the third one is a coherence, which is the multi-core. Some core invalidate your data. Means it modifies your data. That core has the latest version. So in this way, you also have a miss. So there's no conflict is not a target for the prefetching. Because conflict is about your way, your site, your associativity. So the prefetching cannot help you with this type of miss. Prefetching can only help with the compulsory capacity and coherence misses. Because if for the conflict, if you read that piece of data, if you prefetch that piece of data, you still have the same conflict. Because they always go to the same site, they always go to the same way, they will have the conflict anyway. For the data you never met, if you have a so-called oracle prediction, you can reduce this compulsory means for the capacity before the read happens, before the miss happens, you can pre-fetch that piece of data in the cache. So prefetch can also elevate this capacity misses. So there are always two types of challenges for the prefetch. The first one is what to prefetch. The second one is when to prefetch. Um, what to prefetch is easy. You don't want to read the useless data. You don't want to waste the resource. For example, the SRAM, expensive, power-hungry SRAM to store some useless data, the data you are never used. You only want to read the data you actually will use in the near-term future. By near-term future, it's when to fetch. You don't want to fetch it too early because it will occupy the space in the cache. Some more useful data will be evicted in this way. You also do not want to prefetch it too late. Otherwise, after the miss happened, it's equivalent to the read operation, to the cache miss read operation. So too late is also useless. It is not good either. So this is what happens if we do not have so-called prefetch. Assume the y-axis here, assume the x-axis here is the time, and we have a load here. This is a L1 read, so it's very fast. And then we have a means we go to L2. And then we have a DRAM. And then we have a L2 means, and then we go to DRAM. We get the data. So this is the total latency we need to pay to fetch this piece of data. So if we have so-called prefetch, somehow we can predict we need that piece of data at this point. We go to the DRAM directly. When you have this load, basically you get a cache hit in the L1 cache. That's all. So you can see this is our prefetch latency. The latency if we have a prefetch. This is the latency we have no prefetch. And you can see there is a huge difference between these two cases. And the CPU is very sensitive to the read latency. Or if you have a not so accurate prediction, you predict at this time, you need that piece of data. And at this time step, you have the read. But you cannot finish the prefetch until here. So you find the L1 means and the L2 means, you go to the DRAM here, and then at this time point, you find out the access is returned. The DRAM access is returned. Still, this is your total latency. Compared to the the latency without prefetch, you still have a very large improvement. So basically, this is your saving, latency saving. If this figure indicated that even not so accurate prefetching can reduce your memory access latency. Any question? So the prefetch must be accurate and timely. So again, this is corresponding to the two challenges here. The first one is what to fetch. This is about accuracy. The second one is when to prefetch. When means timely. So assume that this is a CPU, this is a core. Without prefetching, you have application execution. The white bar indicate application execution, instruction execution, and this bar indicated the read operation, load. So they are sequential. This is a sequential execution. Do know the instruction execution and memory access are actually sequentialized. If we have a prefetch, we can overlap the execution and the memory access. You can see we can make the memory access predicted. This is the data I need. So this is the memory access. And then we can simultaneously run the code because at this time step, we don't need this piece of data. When we actually need that piece of data here, we can have that piece of data and then we can continue to do the execution. So this is a very ideal case. We totally overlap the instruction execution and the memory load. So prefetching can remove the read operation or load operation from the critical path. Now the critical path only have some instruction execution. So there are these many types of prefetching. We will briefly introduce them one by one. The first one is, of course, the easiest one. The programmer can configure or can do the prefetch. So the compiler or the programmer can insert the prefetch instruction into their codes. You can prefetch some data and put that piece of data in the registers, or you can prefetch the data in the cache. Now I think the x86 Intel CPU or AMD CPU at least support this type of prefetching. Assume this is your application. You have some dependency. You have some basic block A, B, C, and B, C depends on A, the output of A. And in the block C, you actually use two different values. One is R1. The second one is R3. And we have a miss on the R1. This is a miss. So if you are the programmer, you know this is the first time I accessed R2. In this way, you can actually, prefetch it in basic block A. You can do the prefetching, do the read at this time. So when your application execute to this point, you have that piece of data in the cache. In this way, you don't have a miss anymore. So for the register-based prefetching, you have to understand the dependency. Otherwise, you cannot manipulate these registers. There are two types of prefetching. The first one is register-based. The second one is cache-based. So for the first type, of course, you need to understand the register. Otherwise, you cannot manipulate those registers. For the second one, you can clearly insert a instruction, which is I want to prefetch R2 in block A. So in this way, you can also perform a prefetch. So this is one example. You do a prefetching here. I think now x86 instruction set totally support this instruction. The advantage of this software-based prefetching is that programmer have better control on their codes, and you can also use your advanced compiler to do some advanced optimization. We don't need to modify the hardware because the so-called prefetch is just a read operation. You clearly insert a load operation at this point of the execution of your code. The disadvantage is that you can only handle some very simple case. If the programmer has no experience, then basically his or her code is not accurate. He or she may insert that prefetch too late because prefetch itself costs 100 cycle latency. He or she may insert that instruction very late so that the prefetch may not help too much. Or he or she insert that piece of instruction too earlier. that this often lead to a very low accuracy, because when you fetch some data too earlier, that piece of data will occupy in the cache for a very long time. It will occupy some space for the more useful data. So this is not good either. Also, prefetching increase the code footprint. Potentially, it can increase the instruction cache miss. We have some code alignment issue. So, if you are a very experienced programmer, of course, the software-based prefetcher or prefetching can help you a lot. But if you have no experience, then this may not be a good idea. So in this way, for the new programmer, we have to design some hardware-based prefetching or prefetcher. We use hardware to monitor the memory access. So the hardware can do some prediction and then insert some prefetch request to the prefetching queue. The queue is checked when no demand access waiting. Why no demand access waiting? Because you don't want to the prefetch memory access block the real miss access. So you want to give the cache miss a larger priority, so that the memory system can serve those requests first, and then if you have redundant bandwidth, you can do the prefetch. So the prefetcher just look the read operation, look like a read request to the memory hierarchy. But again, the memory hierarchy will give these prefetching requests lower priority, so that they will not block the normal cache miss request. So this special prefetched flag can help you distinguish whether this is a prefetch request or a normal request, so that you can do some QoS, quality of service control. So the prefetcher actually wastes your bandwidth, but can reduce your latency. So it's trade your bandwidth for latency. Extra bandwidth is used only when guessing incorrectly. So if the prefetching accuracy is low, then we use extra bandwidth. Of course, we waste the extra bandwidth. The latency is reduced only when the prefetching accuracy is high. When the accuracy is high, you can reduce the latency. The good news is that you don't have to change the software anymore. You don't have to recompile or change a new compiler. If you still use the same instruction set, you can directly run your code on the new machine, and the new machine with a hardware-based prefetcher can help you performance, can reduce your latency a lot. So this figure indicates where we can put our prefetcher. We basically can put a prefetcher in L1 instruction cache, L1 data cache, L2 cache, and L3 cache, and the last level cache. Last level cache means it can be L3 cache, but it can also be L4 cache. And the real CPU also have a multiple prefetcher. Detect a different access pattern. So it's typically it's easier, for the upper level prefetcher to get a high accuracy, but it's really difficult for the lower level prefetcher to get a high accuracy. Why? Because the access pattern has been filtered by the last level cache. So below this last level cache is difficult, to predict the access pattern. So let's introduce the scheme for the hardware prefetcher. The first one is very simple. We just prefetch the next line plus 1. If we have a miss request for line x, then we also read the x plus 1. Why we can do this? Because we assume that we have a strong spatial locality. The spatial locality means if I read this line, I will also need its neighboring lines, line plus 1 or line minus 1. But in this simple case, we just read the line plus 1, x plus 1. And by doing this, we also need to stop. We also need to be careful. We need to stop at the physical page boundary. Why? This is also a concept that we studied in the virtual memory. So if we go across that page boundary, we will trigger potentially, maybe we will trigger a page fault. So once very simple, lightweight prefetch will trigger a page fault. You don't want to do that because in order to recover that page fault, you need to pay millions of cycles, which can be handled by the operating system. This is not, reasonable. You only have can reduce, even you successfully prefetch that line. That line can only slightly reduce your access latency. So it's not reasonable to trigger a heavyweight page fault. So this x plus 1 scheme can be done very efficiently. Because it's just simple. When you issue a read request, you can fabricate another request by using the address plus 1. And typically, again, in the DRAM, we have the row buffer. So the next line can be easily hit in the row buffer. So relatively, the next line read latency can be very low. So it's very easy to implement this scheme. It works for both the data cache and the data cache and the instruction cache, because the instruction cache typically execute sequentially. Of course, we have some jump, we have some branch, but typically instruction also execute sequentially. And the large data structure may span multiple blocks, multiple lines. This is simple, but may not timely, because we may not use the next line immediately. Maybe we still need hundreds of cycles, and then we will use the next line. But again, you have to occupy one block for hundreds of cycles. This is not a timely design. We can also do a more aggressive scheme, which is next n-line prefetching. This is also very easy. Instead of only read the plus 1 scheme, we can also do the plus 2 and until plus n. You can, of course, define this n value yourself. It can be 8 or 16 or even 32. The n here is called prefetch depth or prefetch degree. So how to select a reasonable n is a very tricky thing. Large n, if you choose a large n, if you know it's correct, then you can benefit a lot. If it's not correct, then you just make the mistake bigger. Because you need more storage for the prefetch lines. This can help you only if you have a very sequentialized application. You do not have the branch too much. All your codes are loops and some sequentialized code. If you use this next n line scheme. This is a simple, and you can also read more lines. So compared to the next one line scheme, it's more timely. How about if you have multiple streams? So previously we only talk about n+1, or I'm sorry, x+1, x+2 until x+n. It's all about x. How about if you have A and B, two different streams, and they intertwined each other, intertwined with each other. You cannot even distinguish them like this: A, B, A+1, B+1. You have some, access pattern like this. How can you handle this? Then you need to use multiple buffer to store the prefetch line. You need a separate independent buffer to track different streams. You can keep next n available in the buffer. On request for the line x, shift the buffer and fetch the x+n+1 into it. So this is one example. For example, this is your CPU, this is your cache, direct mapped cache, and this is your prefetch buffer. You can have a tag to indicate whether this piece of data is the data you want to read. Again, it's similar to the cache. You also have a tag here, but you can use a FIFO, first in, first out, to serve as a stream buffer. The counter here can help you to count whether you reach n or not. Of course, when you do the prefetch, you want to read n lines. The counter here can help you to record whether you reach your prefetch depth or prefetch degree. And if you have multiple streams, of course, you need a separate queues here. So there are 4 queues here. Totally, you can maintain 4 streams here. And of course, you can support those multiple streams in parallel. Until now, we only talk about some sequentialized code, some data structures, spans across multiple data lines. If this is a data line, basically we assume that we, one data structure may occupy these lines, consecutive lines, continuously. But sometimes we need to handle matrix. For the matrix, we have one row, and we have different rows, and we also have different columns. So this is one columns. For this column is actually stored in this way. Each element in this column is not stored consecutively. So one element is not stored consecutively to another element in the same column. So they have some space, and we call this space as a stride. The stride is a fixed value because it's a matrix and it's a column. It's a regular fixed value. So how to handle this case if we want to do some matrix vector multiplication, we need to read this column. How can we do that? We can use so-called stride prefetching. The access pattern here actually follows a stride. For example, we access columns of the elements in a matrix. We access the elements in an array of the structure. We can do two things. The first one is to detect this stride value and then prefetch the depth of n. For example, we can prefetch x plus 1 multiply s, x plus 2 multiply s, and x plus n multiply s. So in this way, we can handle this stride access data pattern. So we need to carefully select the depth of n. If we select a larger n, then we will, it more easier for us, much easier for us to make a larger mistake. The next one is how to dynamically adjust this n. We can use some counter to do that. We can use the counter to serve as the so-called confident. Assume that we just predict that the stride is n. We assign a value to this n. If you always read the data address I predict, then I increase this counter. If you always read the address I predict, which means that I predict correctly. When I predict correctly, I increase the counter. I increase my confidence. When my confidence above some go above some threshold, for example 2 in this case, I do the prefetch. If I made a mistake, I predict wrongly, we decrease this counter. I reduce the confidence. When the confidence go below this threshold, then I stop to do the prefetch. So in this way, we can dynamically control these steps. This dynamic scheme is very important for this stride prefetching. Besides this counter, this confident, we also have the stride. We also have the last address. We always add a stride on the last address to serve as the next prefetch address. If the value I predict is the same as the actually memory access, then I increase the counter. Otherwise, I reduce this counter. So again, this stride prefetcher also have multiple stream. Can also have multiple stream. They can also mingle together. So how to distinguish between each other, how to maintain each individual stream is a question. So again, we can also have a structure like this for different streams, strata streams, but this is very expensive because for each stream we need to have a counter, we need to have a adder. So instead of doing that, we can access to the structure localized to an instruction. We can use this phenomenon to do the prediction. So this access pattern is actually related to your PC. The PC is your program counter, which means that when I execute that piece of instruction, I will do the read operation. So there is some link between that piece of instruction and that read operation. So I can use that instruction to index that read operation. So in this way, I can create some hardware named reference prediction table. I can have a confidence here, a strata value here, a last value here, and a tag here. The tag can store the PC. The PC is the PC counter. So by this PC, I can evaluate whether they are the same strata. If they are the same strata, I increase the counter. Otherwise, I reduce the counter. I'll keep the counter unchanged. When the counter is high, then I have a higher confidence on this stream. I will do the prefetch. Otherwise, I will not do the prefetch. So by the PC value, we can use the PC value to distinguish whether these access belongs to the same stream. If they do belong to the same stream, we can increase the confidence counter. Otherwise, we just decrease it or unchange it. For some more complex data structure, the access are regular but not straight. For example, you have a linked data structure, list or tree. In this way, this is a very notorious problem, which is a pointer chasing. The actual memory layout can be like this. Some data are stored separately. Some data are stored consecutively. But in the logic view, you have a counter. You have a pointer. And this A use a pointer to point to the position of V. By visit a pointer, you can chase the list one by one. But in the memory, the value of A may store here. B may store here. C may store here, but actually, in this case, C is stored here. So they may not be stored consecutively. It's impossible for you to detect a stride. So all you need to do is to use the pointer to do the prefetching. So each memory access, we can read 64 bytes, which is 512 bits. Assume this is the 512 bits. And the 512 bits have different values. 512 bits may include one integer, one long integer, one short integer, one floating point integer, multiple integers like this. So pointers typically looks different. We can take a guess which one is a pointer. And this is, of course, not a pointer. This one is not either. This one is not either. This one is not either. And these two, maybe they are pointer. Why these two are, these two are pointers? Because they are irregular. The pointers stores the memory address of that piece of data. For example, the pointer of A stores the memory address of element B. The element B is stored in some random memory address. So it cannot be a 0 or 1. These are very regular normal value. It must be a very large, very random value. So by the value of the pointer, you can, by the values of the integer, you can, of course, take a guess whether they are the pointer or not. So if you detect some value, maybe the pointer, you can try to read the value stored in in the address of these pointers. And of course, you need the help of TLB, because you do not know the physical address. These are maybe only virtual address. The value only indicate the virtual address. So the pointer chasing prefetcher is actually easy to implement. You don't need some extra hardware overhead to store the patterns. For example, the confident, you don't need that confident stride counters. You just need to do the prefetch and then decode the pointer, and then based on the current pointer value, do the next prefetch. So this is the pointer prefetching. For the stride prefetch, you can sequentially issue prefetch request x plus n, x plus 2n. You can consecutively issue the prefetch request, but for the pointer, only you read the data of B, you can decode the pointer of B. You can read the value of B. So the prefetcher have to be, consecutively do the prefetching. Some more complex application may not even have a pointer. So in this way, you have to detect a so-called temporal correlation. The so-called temporal correlation means if E followed D in the past, when we see D, we will prefetch E. So based on some previous experience, based on some past experience, we can do some prefetching. And this is a so-called temporal correlation, because there's no spatial information. There's only temporal information, the time. We can create a correlation table like this. If we see some access pattern like this, E is always followed D. This is D. E is always followed D. So we store D here. Next time when we see D, we directly prefetch E. And also, E also have some, temporal correlation. For example, in this, in this case, F followed E in the past. So F followed E in the past. When we prefetch E, we can also continue to prefetch F. This is also the prefetch depth. We can define the N until we reach that N, we can stop. Because the access pattern is so complex, sometimes we need some prediction model to do the prediction. For example, Markov model. Nowadays, you can even train a deep neural network to do the prediction, to do the prefetching. And someone has already done that. And these values can help you to record the edge value of the Markov model. And based on the Markov model, you can predict which request follow which request. And of course, multiple requests can follow one request. So you have a number of candidates. This is also called a breadth. When you fetch one value, it also have multiple candidates to prefetch. So the recursive breadth and depth grows exponentially. This is another issue. Maybe multiple candidates follow one request. If you see this request, you will prefetch multiple candidates. Among those candidates, each candidate may have multiple candidates followed. So how to define the depth and the breadth are very important for the accuracy and the timing of the prefetching. We can also increase the history length. In previous slides, we only consider one: who followed whom, which followed which. Only one step. But in some cases, we can maintain a long history list for one single candidate. We can use the history hash to do the lookup. For example, this is a depth first search on this tree. And this is the access pattern. So we can use two different access to predict the next access. In the previous slides, we only use one request to predict the next access. But here we can use two access. When we see A and B, when we see this pattern, we can read D. This is very useful for the DFS traversal. When we see B and D, we do the prefetch, we prefetch B. Of course, when you increase the history list, you can achieve better performance, you can achieve better accuracy, but the storage overhead also increases exponentially. And all previous three slides explain the correlation on spatial locality. I'm sorry, the temporal locality, temporal correlation. In this class, we will introduce a spatial correlation. The spatial correlation indicates some irregular data layout. So you cannot conclude or summarize the data layout like stripe. So it's non-stripe. All is sparse. It cannot capture by the spatial locality. It has some fixed pattern. Fixed pattern means repetitive. It will repeat multiple times in the same way. For example, in some database page in memory, basically all the page have a similar data layout. You will use only several fixed points in the page for all the pages. And you can see there's no stride, and it's sparse. On one page, you only use several values, which is tagged as red in this case. So because each page has a similar data layout, we can use the spatial correlation information to do the prefetching. We can logically divide the memory into regions. We can identify the region by the base address. So in this case, it's very simple. If it's a database page, it's very simple. Each logic region is just one page. We can store some spatial pattern counter, bit counter in the correlation table. For example, we can divide the entire page into 4 kilobytes page divided by 64 bytes. Totally, we can have another 64. So in one page, we have 64 byte blocks. We can use 64-bit counter. No. This is so-called bit vector. 64-bit vector to indicate which block is useful and which is not useful in this case. And this block, this bit vector can be indexed also by the PC. Because when you execute that piece of instruction, you will have that memory access pattern. So in this way, it's similar to the temporal spatial correlation. So until now, we introduced several prefetcher. We introduced the next one line prefetcher. The first one is a software prefetcher. The second one is a next n-line prefetcher, next one line prefetcher, next n-line prefetcher, stride prefetcher, multiple stream prefetcher, some prediction-based prefetcher, temporal locality prefetcher, and a spatial locality prefetcher. We introduced so many prefetcher. So how to compare each one against another one? So we defined several metrics. The first one is coverage. So the prefetched heat divided the base misses. The second one is accuracy, prefetched heat divided by total prefetch. The last one is timeliness, the latency of prefetched block divided by the heat latency. We can also evaluate the pollution, bandwidth cost, power, area, and hardware overhead of the prefetcher. I think the first three metrics are the most important one. if you have a very good prefetcher, then you do not need a very large cache. Because the goal of a prefetcher is to increase the data hit rate. And the larger cache, the goal of a larger cache is also increase the hit rate. If you have a very good prefetcher, you don't need to have a large cache. If you do have a large cache, then basically you don't need a complex prefetcher. You can use a very simple prefetcher. That's the trade-off. Because the prefetcher is not free, complex prefetcher has a lot of history, buffer, counter, confident counter, a lot of logic. It also introduces significant area overhead and energy consumption. Again, after we learned so many prefetchers, can we answer these two? The first question is, this is the basic two challenges for the prefetching. The first one is what to prefetch. We can use predictor to predict some regular pattern. We can also use the predictor to predict some correlation pattern, which is not regular, which is irregular. We can capture the spatial and temporal patterns. When to prefetch? We can prefetch on every read operation, on every miss operation. We can also prefetch on, if we get a very high prefetch accuracy, we have the confidence counter, positive feedback flow. We can store the data of the prefetcher in some dedicated buffer, prefetched buffer, or some cache. The last one save area and power because you can share the same cache. But if you have a low cache, if you have a low prefetch accuracy, then you actually introduce more cache miss. The first one is good. You have a dedicated buffer to store the prefetched data. But again, it introduces extra overhead. Then these two are also have some trade-off. In the commercial CPU, we have a L1 cache, data cache prefetch, L2 data, L1 data prefetcher, L1 instruction prefetcher, and L2 prefetcher. These are very simple prefetcher. I don't think we have a commercialized temporal or spatial correlated prefetcher. Those you can see those applications those prefetcher only designed for some special application like database. Only database have those data pattern, access pattern. Any question? So if no question, we can stop today. Thank you very much.
Thank you.